Hey everybody, it's Monday, October 19th. Hope you all had a nice weekend. For today's video, as you can see here in the aim, we are going to discuss how we can use our understanding of horizontal projectile motion to answer conceptual projectile motion questions. So as you saw last week in the video that was posted on Friday, we went through some basics about horizontal projectile motion, talked about some of the concepts, and then solved a problem. And you may remember at the end of that video, I said, ordinarily this would be the point where I'd have you solve one of these problems on your own, but because the video's getting kind of long, we'll save that for the next video. Well, this is the next video. And so the first thing I want you to do for today is to solve one of these problems on your own first before we get into the conceptual questions. And so this problem, once again, comes from the old textbook. Doesn't really matter to you because you don't have a copy of that textbook to avail yourself of, but the whole reason why I decided to keep these problems from when we used to use this old textbook is because there's not that many of these in the two-dimensional motion packet, surprisingly enough. And so I wanted to use these so we didn't have to use up some of those problems, basically, so you could save them for homework. And so this problem is 3.36. It says rock thrown horizontally from the top of a radio tower lands 17.0 meters from the base of the tower. If the speed at which the object was projected was 9.50 meters per second, how high is the tower? So the first thing I'd like you to do here is pause this video and make the chart. And then when you hit play, we'll talk about the chart only, because there's no point in you solving this problem if you have the wrong chart. And so let's just at least make sure we all have that straight first. Go ahead and pause here and make the chart, and when you hit play, we'll go over it. So notice here they tell us that the rock lands 17.0 meters from the base of the tower. If you're properly visualizing the situation, then what you'd realize is that if the tower looks something like this, then the distance from the base of the tower where this rock lands is the horizontal position, essentially. And of course, the speed here, because this is, as it specifically says, a horizontally launched projectile, we know that that 9.50 meter per second velocity is a horizontal velocity. So your chart should look something like this. Of course, we call the initial positions in both dimensions 0 meters. That just makes our life easier to say the origin of the coordinate system is located where the object begins. And so essentially what we're saying is our coordinate system, our coordinate axes begin there. And there's our x-axis. And there's our y-axis. That's the basic idea. So we call those initial positions 0. The horizontal final position is 17.0 meters. The horizontal v0x and vfx velocities are 9.50 meters per second as given in the problem. And the initial vertical velocity is 0 meters per second. Of course, that's always going to be the case for these problems, because if they are launching the projectile horizontally, then they're not launching it vertically. And so the initial vertical velocity would be 0. The x direction acceleration should be 0 because there are no horizontal forces. And since there are no horizontal forces, there are no horizontal accelerations. And the vertical acceleration, of course, is our good old friend, negative 9.8 meters per second squared, which is the acceleration due to gravity. Now, I don't really want you to do this in parts. I just want you to go solve it. So the question here, remember, is asking how high is the tower? So go ahead and pause this video here. Do what needs to be done for you to determine the height of the tower. And when you hit play, we'll go over it. Okay, so the first thing you need to do, as I think I mentioned in the last video, which is generally always the case for a horizontally launched projectile, is you need to find the time. because as I mentioned last time, the time is the bridge from one side of the chart to the other side of the chart. And to me, I think, and I hope you would agree, it seems obvious here that the x side of the chart is going to be the side of the chart that you want to use to find the time, because it's literally the only thing you don't have over here. And so to start this off, we have to start by finding the time. And so to do that, we are using the information from the x side of the chart. And so the time is our unknown, and the only equation that works in the x direction is the position equation. X equals x naught plus v naught x times t plus 1/2 ax t squared. Now, because we said the initial x position is 0 and the x acceleration is 0, those two terms immediately go away. They die. And so we're just left over with x equals v naught x times t. And to solve that for the time is pretty simple. You just take the x final position, essentially the x displacement, and you divide it by v naught x. And so we have our 17.0 meters divided by 9.50 meters per second. And we end up with a time of 1.79 meters. Oh, geez, 1.79 seconds. It is a time, and so the unit is seconds. And of course, we leave it as a number with 3 significant figures, because all of the other numbers in the problem are given to 3 significant figures. Now, if you want, you could go add this into the chart. You don't have to, but if you want to, you can. Now, every single year when I say that, everybody asks a question, and that question is, well, if I don't include the time back into the chart, since the chart is how I'm writing my knowns, then doesn't that mean I'm going to lose a point on the next part of the problem when I need to use the time to find something else? And the answer is no. Your knowns for any multi-part projectile motion problem either need to be in the chart or the answer to a previous part of the problem. I am never going to look at your work for, like, let's say part B was to determine the height of the building after part A was to find the time. And I'm never going to look at your work and see you find that the time is 1.79 seconds and then be confused about why you're using that time afterwards. So it's perfectly fine for you to just leave it as is. And now that we have the time, and I'm just going to do this for here just so we can have the discussion about what equation is supposed to be used. Now that we know that the time is 1.79 seconds, and I'll just put it over here too. Now we need to find the final position, and we know the initial position, we know the initial velocity, and we know the acceleration, and we know the time. So the equation that would work best to do this, of course, is the position function again. And so the position function here to find y, the final y position, is going to be y equals y naught plus v naught yt plus 1/2 ayt squared. And so when you cancel out all the terms that go to 0, which is the initial y position and the initial y velocity, because we already said those things are 0, we end up with y equals 1/2 at squared. And so you just plug in the acceleration, negative 9.8 meters per second squared. You plug in the time, and you end up with a final y position of negative 15.7 meters. Now, it's important to realize one thing about this calculation. Our calculation does not directly give us the height of the building, but like common sense dictates here, if this object starts at the top of the building and then the spot where it ends up is 15.7 meters below the starting point where y equaled 0, then that means the height of the building is 15.7 meters. And the only reason we don't put a negative sign on the height is just because, height, I guess, if you really want to look at it this way, is a scalar. And so it doesn't have a direction. I mean, I guess you could say the direction of all heights is up, but that's not really how we think of it. And so we could just put at the end here, the height is negative 15.7 meters. Of course, if you don't put that, that's totally fine too, because logic and common sense dictates that when you put the final position as negative 15.7 meters, you're effectively telling me that's how tall the building is. All right. And that's it for that one. So if you go to the sheet that was attached to this post, there should be multiple sheets. You want to be very careful about opening the right one. I guess I'll show it to you here. The sheet is called Horizontal Projectile Motion, Conceptual Understanding, number 1. The first problem on that sheet is B2 RT15, rifle shots, time to hit the ground. Notice the number has always been B1 so far. This one is B2 because now we are in two-dimensional motion. And so this problem says the rifles in the figures are being fired horizontally, straight outward, as if you don't know what horizontally means, off platforms. The bullets fired from the rifles are all identical, but the rifles propel the bullets at different speeds. The speed of each bullet and the height of each platform are given. All of the bullets miss the targets and hit the ground. Your job is to rank the time it takes the bullets to hit the ground. It's very important for everybody to remember one thing, and this is the only thing I'm going to say before I have you pause this video and answer this question. In the video on Thursday of last week, maybe it was Wednesday, I forget now, there was a video about proportional reasoning. And I said in that video, basically every single time you solve a conceptual problem in this class, for every other unit that we are ever going to cover, you got to use this. Well, you have to use it. So keep that in mind as you answer this question. This question says, rank the time it takes the bullets to hit the ground. Go ahead and pause this video here, and when you hit play, we'll go over it. Okay, so as I mentioned, I think the best way to go about answering these problems is by thinking about proportional reasoning, because a lot of people get hung up with trying to answer the question and then come up with what seems like a good explanation. And the great thing about proportional reasoning is that you don't actually have to do that. If you come up with the reasoning first, the answer completely falls into place. The question says, rank the time it takes the bullets to hit the ground. Now, you don't actually have to calculate it, but of course the question is, how would you if you did have to? Well, if you had to, you'd use the displacement equation or the position equation. And I'm just writing this here to save room with the delta y instead of the y and the y naught. Of course, if you subtract y naught over to the left side, you get y minus y naught, which is the definition of delta y, so same thing. And here, the initial velocity in the y direction is 0 because the bullets are fired horizontally, straight outward. And so the equation that we end up with is delta y equals 1/2 ayt squared. And if you solve that for t, you get the square root of 2 delta y over ay. And so according to that equation, the time is directly proportional to the square root of the vertical displacement. So if the vertical displacement is larger, then the time is going to be larger. The acceleration obviously is a non-factor, even though it's in the equation, because that's the same for all of them. So with the same acceleration due to gravity, which is the case, a higher height is going to give you a larger time. And so that means C and B, because they're the same height, are the largest, then D, and then A. And what's nice about this is now you don't have to think, oh my gosh, how am I going to explain this? The thinking that you did in the beginning just to come up with the answer is the explanation. And so a possible explanation looks like this. Since the time of flight is directly proportional to the square root of the height, when the height is larger, the time of flight will be larger. Now, despite the fact that I wrote this explanation myself, I think this explanation is missing two things. The first thing I think it's missing is something I've already addressed. It's saying that the acceleration is the same. Because saying that like the time of flight is directly proportional to the square root of the height is actually only true if the accelerations are the same. You can't make that kind of comparison if you're comparing an object like on the Earth to an object on the moon, because, well, then the time would also be dependent on what the acceleration due to gravity is. But I think this explanation is also missing something else. And I want you to think about what that something else is as I type out what I think should be your full explanation. And I think this explanation is missing something else, and I want you to think about what that something else is as I type out this explanation, or what I think should be the full explanation. So since the time of flight is directly proportional to the square root of the height, by the way, mentioning that it's the square root of the height and not the height is super important. When the height is larger, the time of flight will be larger, and the gravitational accelerations are the same. Additionally, now what else is missing? I don't think these should go unaddressed when they're giving them to you, right? Because they're clearly trying to trick you into thinking that matters by giving you the same height in C and B, but giving you different launch speeds. And so we could say, additionally here, the initial velocity of the bullet doesn't matter because the horizontal motion of the bullet has no effect on its vertical motion. And that, I think, is a much more thorough and comprehensive explanation. And I'd like you to pause this video here and take a moment to add whatever from this is missing in your explanation. And when you hit play, we'll move on to the next one. The next one on the sheet is B2RT15. It says two toy trucks roll off the ends of identical tables. The speeds and the masses of the trucks are given. Will truck A be in the air for a longer time, a shorter time, or the same time as truck B before it reaches the floor? Now, does everybody see how this is the same one? I hope you basically see this is the same question. They ask stuff like this a lot on the AP test. And so again, your basic idea here is that because the equation says that the time is equal to root 2 delta y over a, the time is directly proportional to root delta y and has nothing to do with v naught x or a. And so the answer here would be the same because the heights are the same. And the reasoning would be identical to the reasoning from the last problem. And that's really all that needs to be said about that. Also, because they're giving you different masses, we should also say the mass has no effect on the time of flight. And that's actually a really important point because they do ask about that a lot. So I'd like everybody to take a minute to write that down. pause the video here, and when you hit play, we'll move on to the next one, an actually different problem. Okay, so moving on to the back of the sheet here, you see the next problem on there is B2 CRT 12, projectile motion for two rocks, velocity versus time graphs. It says here 2 students throw 2 rocks horizontally from a cliff with different velocities. Both rocks hit the water below at the same time, but rock B hits farther from the base of the cliff. Notice it makes sense here that they hit at the same time based on everything we just said, right? So it says use coordinates where up is the positive direction and away from the cliff is the positive horizontal direction. And the origin is at the top of the cliff at the point of the release. I actually really like a diagram like that because I think like visualizing the coordinate axes like that just like makes a lot of sense. It's a good visualization. So the release point is the origin, and we see the situation look like this. Now, the question here says sketch below the velocity versus time graphs for each rock. Rock A, remember, is the one that lands closer, and rock B is the one that lands farther. And so I want you to do a couple of things here when you go ahead and pause here in a moment. The first thing I want you to do is I want you to sketch the graphs. The second thing I want you to do is to make sure your graphs are showing the magnitudes correctly. Remember, this is like a graphical translation where you make your sketch and then you check and see if the quantities are shown with the appropriate magnitude. And then to finish it off, I want you to explain your reasoning. And when you're explaining, I want you to do 2 things. I want you to explain the commonalities between the graphs, and I want you to explain their differences. This is going to take you a little while. So go ahead and pause this video here, and when you hit play, we'll go over it. Okay, so your horizontal velocity versus time graphs should look like this. I'm sure this is not that hard to see, but there's my line for A, and then there's my line for B. Note the similarities. Note the differences. And then the velocity versus time graphs should look like that. Now, of course, the vertical velocity versus time graphs are identical. So that's a pretty easy explanation. But explaining the differences in the horizontal ones is a little trickier. But the explanation would look something like this. Notice there, I'm stating the equation. So I start with the x graphs and I say x equals v naught x times t. Since the acceleration in the x direction is 0, both rocks have a constant horizontal velocity. And you could explain that by talking about features of the graphs. The slope of the graph is the acceleration is 0, so the slope is 0. And then I wrote, since x is proportional to v naught x, rock B has a larger horizontal velocity. And that's why it's shown as a little higher on the graph. Of course, for the y graphs, the y direction graphs, since both rocks have the same vertical acceleration due to gravity and are both dropped from the same height, dropped, of course, is in quotes because it's thrown, but the v naught y is 0, they will have the same vfy, and of course, they have a constant slope because there's a constant vertical acceleration. Take a moment to write that down, and when you hit play, we'll move on to the next part. Okay, so the next part now asks you to draw the acceleration versus time graphs. And I don't want you to go nuts about the explanation here because the explanation doesn't need to be that complex because the answer is pretty simple. Take a minute to pause this video here and sketch those graphs. And when you are finished, hit play and we'll go over it. Okay, so your graphs should look like this for the horizontal Notice the only reason I made those super dark is because they are on the 0 line. And so I wanted to distinguish them from the origin. And then for my vertical graphs, they look like that. It's really not a whole lot to say. There's no horizontal forces after the launch, so there's no horizontal acceleration. And since both rocks accelerate due to gravity, they both have the same vertical acceleration. That's it. All right, take a minute to write that down. And when you hit play, we'll move on to the next sheet. Okay, and that brings us to sheet number 2. Now, the first two problems on sheet number 2 are really, really similar. And so I actually want to jump to the second one. This would be B2 WWT22. It says horizontally launched toy trucks, time and air 2. And it says a toy truck is launched horizontally from a table. In case A, the toy truck hits the floor a horizontal distance 2x from the edge of the table. And in case B, the toy truck hits the floor a horizontal distance x from the table. A student comparing the time the trucks are in air in these cases states the farther you go, the longer it takes to get there. The truck in case A will be in the air longer. What, if anything, is wrong with the statement? If something is wrong, identify it and explain how to correct it. If the statement is correct, explain why. I'd like you to take a few minutes to pause this video here, answer this question, come up with your explanation, and when you hit play, we'll go over it. So your answer should look like this. The time in air is not determined by the horizontal displacement, but by the vertical dimension. According to the equation y equals y naught plus v naught yt plus 1/2 at squared, the time is equal to 2 times y over ay. That should say ay. Since the time in air is proportional to the height, both trucks will stay in air for the same time. Now notice I said proportional and not directly proportional. That's the thing you have to be careful of. If you say the time is proportional to the height, that's fine. But if you say directly proportional, that implies a linear relationship. And so then you have to say it's directly proportional to the square root of the height. And so just make sure you're describing these things accurately. Take a second to pause this video here and write that down. When you hit play, we'll write a little note about what I just said, and then we'll move on to the next one. Okay, let's just write a quick note about what I just said. Note, the phrase proportional is a general phrase to imply that as one quantity increases, another quantity increases as well. The phrase directly proportional, however, implies a linear relationship, and so squares or square roots must be accounted for. So using the equation delta y equals 1/2 at squared if the initial velocity is 0, and then you solve this for t equals 2 delta y over ay, you can say t is proportional to delta y, because that means as delta y increases, the time increases, and that's certainly true. But if you say this, the time is directly proportional, or use that symbol, you have to say is equal to the directly proportional to the square root of delta y, because that implies a linear relationship, and you are only going to see a linear relationship on the graph if what's plotted is the square root of delta y and t. Take a minute to copy that down, and when you hit play, we'll move on to the next problem. The next one is a big, long one. It's B2 LMC T14. Dropped practice bomb, horizontal distance traveled. It says an airplane is flying 1,200 meters above the ground at a speed of 200 meters per second. It drops a practice bomb that hits the ground after traveling a horizontal distance of 3,130 meters. For each of the changes below, use the choices 1 through 5 to identify what will happen to the horizontal distance the bomb travels while falling compared to the situation above. Keep in mind here, in this particular example, with all these variables, it travels 3,130 meters. And so the 5 changes are the horizontal distance is going to be greater, less than, equal to, it'll be 0, or it's impossible to tell how it'll affect the horizontal distance. And by the changes, they're saying only these features are modified from the given situation above. So I'd like you to start here with part A. How will the horizontal distance traveled by the bomb change if the plane's speed is tripled? Take a minute or two to pause this video here, come up with an answer and an explanation, and when you hit play, we'll go over it. So it says here the plane's speed is tripled. And when you see words like tripled, you should know this is just going to be a proportional reasoning problem. The horizontal distance is v naught x times t. The horizontal distance is proportional to the horizontal velocity. And so if the horizontal velocity increases, that means the horizontal distance will increase too. The answer here would be choice 1. Delta x is directly proportional to v naught x. If you want to pause this video here and write that down, go ahead and do that now. Then we'll move on to the next one. Okay, part B says the plane is climbing straight up at the release point. Now, I think we should probably just go ahead and skip this one, because every single year, the second I say what part B says, some kid raises their hand and says, "But mister, the plane is going to stall if it's climbing straight up." They assume that this would be given to physics students and not plane school kids. But the answer here is choice 4, right? The horizontal distance would be 0 if the plane was climbing straight up. If you would allow that ridiculous situation to enter your mind, that would just mean that the plane would have no horizontal velocity at all. So the bomb would have no horizontal velocity at all. And so it would essentially just be in free fall. And so the idea is, since v naught x is 0, x is going to be 0 since they're proportional. Let's move on to part C. That's one I really want you to answer, though. Part C says the plane is flying in level flight at an altitude of 1,100 meters. This one requires a little bit of explanation. Go ahead and pause the video here. Come up with an answer and an explanation for part C. And when you hit play, we'll go over it. For part C here, the part that's complicated about part C is that the equation for the horizontal distance doesn't have the height in it, right? And that's what they're telling you is changing here. So what you really needed to do for this one is sort of go about this in 2 steps. So according to the equation that we have for the horizontal distance, delta x is equal to v naught x times t. And so that means delta x is directly proportional to t. But what does that tell me if I don't consider what happens in the vertical direction? Well, in the vertical direction, we have our equation, and I'm simplifying this because we've said this like 100 times already in this video. The v naught yt cancels, blah, blah, blah. So we have t equals root 2 delta y over ay, which tells me, of course, as we've mentioned already in this video, that the time is directly proportional to the square root of delta y. If you really wanted to, although I think it's a bit of a stretch, you could say that delta x equals v naught x times the square root of 2 delta y over ay. And so in a really weird way, despite the fact that we've been saying the horizontal motion has no effect on the vertical motion, you could get away with saying that delta x is directly proportional to root delta y. Because that seems to violate like that fundamental rule about projectile motion, that the horizontal and the vertical are independent of one another, I do not recommend this. Because it could convey to somebody grading your AP test that you don't really understand a concept that you do actually understand. And so the basic idea is the time is dependent on the vertical distance. And so whatever happened to the vertical distance, well, that's going to happen to the time because they change together because they're proportional. And then whatever happened to the time is going to happen to delta x because they are proportional. And so if you remember here in the beginning of the problem, it said that the plane was originally flying at an altitude of 1,200 meters. Now it says it's flying at an altitude of 1,100 meters. So the height decreased. And so what I wrote here is not that complicated. Since the height will be lower, the time in air will be lower because they're proportional. T is directly proportional to the square root of delta y. Since the time will be lower, the horizontal distance will be lower because they're proportional as well. Now, I didn't do it here because I needed to make these large enough to be able to be displayed on the smartboard in school and seen by everybody in the room, but you should be using those proportional symbols. And if we were in class in person right now, I would be mentioning that, and so I'm going to mention that here. You should say, next to where that equation is, t is directly proportional to the square root of delta y, and x is directly proportional to t. Take a minute to pause this video and write that down, and when you hit play, we'll move on to the next part. Moving on, part D says the mass of the bomb is increased. Take a minute to pause this video here, answer the question, explain your reasoning, and when you hit play, we'll go over it. Okay, for part D, they're talking about the mass of the bomb increasing. Quick answer here. The answer is choice 3. It's going to have no effect, no change in the horizontal distance because the mass doesn't affect anything. It doesn't affect the gravitational acceleration, so it doesn't affect the time, and so it doesn't affect the range. Dunzo. That one is supposed to be quick and easy. Let's not go too nuts about that. The next part, and this is actually the last part, and a question that I like a lot because it's an interesting little thinker as well, is part E. It says the bomb is thrown from the plane with a vertical downward velocity of 15 meters per second. How is that going to affect the horizontal distance? I want you to take a minute to think about this one because this one's a good one. Pause the video here, think about this one, and when you're ready, hit play, and we'll go over it. For this last one here, the answer for E is 2. Since the plane has a downward velocity, or really since the bomb has a downward velocity because they throw it, either way it would be the same though. It's relative, right? Since the plane or bomb has a downward velocity, the time it's going to take to reach the ground is actually going to be less. Because it has some initial velocity, something is going to be subtracted from the final velocity. And so that means the time is going to be less. And since the time is less, the total horizontal distance will be less because delta x is directly proportional to the time. So notice, this proportional reasoning stuff comes up a lot on these AP style questions. And the sooner you get with explaining things using proportional relationships, the easier time you're going to have this year, and the easier time you're going to have on the test. Because believe it or not, that's actually what a lot of the free response question on this test actually is. Okay, and that brings us to the third and final sheet and the last problem of the day, B2CT25. It says here, 2 identical rocks are thrown horizontally from a cliff with different velocities. The rocks are thrown at the same time and shown below while they're still in air after a few seconds. It says, will the magnitude of the horizontal velocity of rock A be greater than, less than, or equal to the magnitude of the horizontal velocity of rock B? I'd like you to take a minute here, pause this video, and when you hit play, we'll go over it. So for part A, they're asking if the magnitude of the horizontal velocity of the rock A, will be greater than, less than, or equal to the magnitude of the horizontal velocity of rock B, and the answer here is less than. The range, dx, that horizontal distance, is dependent on the initial velocity. And so since rock A has a smaller range, it has a smaller initial velocity. And of course, you should be mentioning that that's because they're directly proportional. Now, I didn't write that on this key in any of these answers because, as you can see here, this key is quite old. But the idea is because the horizontal velocity is proportional to the displacement, the fact that A has a smaller horizontal displacement means it has a smaller initial velocity. Take a minute to pause this video and write that down, and when you hit play, we'll move on to part B. Part B says here, will the magnitude of the vertical velocity of rock A be greater than, less than, or equal to the magnitude of the vertical velocity of rock B? Take a minute to pause this video here, come up with your answer, come up with your explanation, and when you hit play, we'll go over it. For B, the answer here is 3. They're equal. The objects accelerate vertically at the same rate. So every second, the final velocity of the objects are the same, since they start at the same height at the same time. And so the equation that you can cite here could be VFY equals AT. Since they've been in air for the same time, they have the same vertical velocity, because VFY is directly proportional to T. Take a second to pause this here. You could write that down, and when you hit play, we'll move on. Okay, moving on to the next one. Part C says, will the magnitude of the horizontal acceleration of rock A be greater than, less than, or equal to the magnitude of the horizontal acceleration of rock B? And question D is actually about the vertical acceleration. So why don't you pause this video here, go ahead and answer part C and part D. Notice those are the last parts on this sheet. When you hit play, we'll go over both of those parts, and that'll be it for today. Okay, so these parts are pretty straightforward. For part C, it says, will the magnitude of the horizontal acceleration of rock A be greater than, less than, or equal to the horizontal acceleration of rock B? They're the same. The horizontal acceleration in the absence of forces is 0 for both rocks, for sure. And there's not really any equation that needs to be cited there. The horizontal acceleration, 0. No forces. Dunzo. Choice 3. And similarly for D, they both accelerate due to gravity at a rate of negative 9.8. Let's pretend that 1 is not there. At a rate of 9.8 meters per second squared. All right, guys, that's it for today. I hope you sort of got a sense of how these proportional reasoning problems are going to look for horizontal projectiles, and got a sense of the kinds of conceptual things that they focus on when it comes to horizontal projectiles. Notice that height and the time thing comes up over and over and over again, and you'll see that on the AP classroom questions when we start to do those as well. And so hopefully this was some good practice and gave you some familiarity with the kinds of problems you're going to have to solve. All right, guys, take it easy.